Hello friends, in my previous video we have derived the expression of built-in potential or the barrier potential of a PN junction which is open circuited. Now we will see the expression of electric field in open circuited PN junction. Then we will see the potential variation across the junction, and finally we will find the width of the depletion layer in open circuited PN junction. So let us again consider we have an open circuited PN junction like this. This is the open circuited PN junction you have. This is the junction. This is P side. This is N side. This is the depletion layer on P side which has negative bound charges, and this is the depletion layer on N side which has positive bound charges like this. This is your depletion layer on or across the junction of the diode. These are the terminals of the diode. This is the metallic contact we have already discussed. This is metallic contact. Now we will see the variation of electric field, but you can just see in the open circuited PN junction on P side I have the negative bound charges. On N side I have the positive bound charges of the impurity atoms. So here if you see the charge density in the depletion layer, this is the junction. You can draw the that line showing the junction. So here this is the charge density rho. This is the junction depletion layer on N side. This is the boundary of depletion layer on P side. So here you can draw the variation. The charge density on N side is nothing but positive. So this is positive. What I am assuming, the bound charges, the charge, you can say the positive charge is ending abruptly at this boundary. Similarly on this side, if you see the charge density, it is negative on P side. So how to find this charge density in this? If you know on this side, if you know the on N side we have donor concentration. So if on N side I know the donor concentration, this is nothing but donor atoms, donor ions. So the donor atoms per unit volume is what? Donor concentration multiplied by the charge of one electron, or you can say charge Q equal to 1.6 into 10 to the power minus 19, that is positive charge equal to magnitude in magnitude of electron, you can say. So what is the charge here? The donor concentration, or the not only charge, I'll say the charge density. Charge density will be what? Donor concentration, that is number of donor atoms per unit volume, multiplied by charge of each atom. Charge of each atom is Q, suppose. So Q multiplied by donor concentration is nothing but charge density. I repeat, that is Q into ND. ND is donor atoms per unit volume multiplied by charge of each atom, so that becomes the charge per unit volume. Similarly on this side, minus y, it is negative, into now the acceptor concentration multiplied by charge of each electron, or not on charge of each ion rather, so minus Q into Na, that is the charge density on P side. These are bound charges of what? Acceptor atoms, bound charges. This is positive charge of donor atoms. So donor atoms per unit volume multiplied by charge of each atom is charge per unit volume on n side. Similarly, number of acceptor atoms per unit volume multiplied by charge of each atom is nothing but concentration, charge concentration on p side, and this is what you have, that is the charge density. Say this is direction x. Why? Because I am assuming the diode is placed along x axis with its junction coinciding with x equal to 0, that is origin. I hope the concept is clear. This is open circuited bar having positive charge density on this side of the layer, depletion layer, negative charge density on this, and this is your variation. Now we will see the variation of electric field in the junction area. And what is the direction? Electric field is always from positive charge to negative charge, so electric field inside the junction will be from this side to this side. So this is the positive direction. This is positive direction, but if you move from this will be negative of E. Now there is important equation we study in case of electromagnetics, that is called Poisson equation. The Poisson's equation is defined for volumetric charge distribution. Whenever there is charge in the volume, we define the Poisson's equation. That Poisson's equation for volumetric charge distribution, I repeat, that is Poisson's equation for space charge. Why? Because this is your transition region, so charge in this is called space charge. So the Poisson's equation for space charge distribution is given by, that is del square V is equal to minus rho by epsilon. This is nothing but your Poisson's equation for charge in the depletion layer. Now if you remember the Cartesian coordinate system, this del square E in Cartesian coordinates is given by, that is d2v by dx square plus d2v by dy square plus d2v by dz square is equal to rho by epsilon. But please remember this is minus, negative. Fine. Now this charge is varying in this direction, that is x direction, but if you consider three-dimensional space, there is no variation of the charge in y and z direction. That is our assumption. The charge inside the depletion layer is varying only in this direction, that is x direction. So for we'll be assuming let variation of V is 0 for y and z directions. Why? Because we are just assuming that charge is varying only in x direction. Therefore d2v by dy square and d2v by dz square is equal to 0 because of that assumption. Now this Poisson's equation can therefore be written as d2v by dx square is equal to minus rho by epsilon. That's your Poisson's equation for depletion layer, depletion region. Now there is important relationship between electric field and potential. The electric field in depletion layer can be related to voltage E is equal to minus dV by dx, that is known as potential gradient. Electric field is what? Negative of potential gradient. So here E is minus dV by dx, so what I can write is this gives dV by d by dx of minus E. Why? Because dV by dx can be separated. This is equal to minus rho by epsilon. So I'll rewrite this equation again. So what do we get? We get here dE by dx is equal to minus rho by epsilon. Or now interesting point, please see this. Let us see the width. This is W. Total width of the depletion layer is W, please remember. The width of depletion layer on P side is suppose WP, that is what I assume, and width of the depletion layer on N side is suppose WN. So what will be X here? X will be minus WN here, and it will be plus this is minus WP here, and it will be plus WN. The x-axis, the coordinate of x-axis at this is minus WP. Coordinate of y-axis at this point is plus WN. So if you see the charge density on positive side is what? That is plus Q and D. From where to where? From 0 to plus WN. So what I'll say, rho is equal to, I'll start from this side rather, rho is equal to what? Minus Q and A for which range of x? When x is greater than or equal to minus WP and less than or equal to 0. Another point. This is equal to plus Q and D for which range of x? X greater than or equal to 0, less than or equal to WN. So what I have, the charge density across the junction, this was a question which appeared in engineering services prelims, the distribution of charge across the junction. And remember, if your charge density is varying abruptly from one side of the junction to another side of the junction, that is called abrupt PN junction. It is also called step graded PN junction. When there is a sharp sudden change of the concentration, sudden change of the charge concentration of the charge carriers from one side of the junction to another side of the junction, that is called abrupt or step graded PN junction. So this is example of step graded PN junction or abrupt PN junction. So what I find is your concentration is varying suddenly across the junction here. So that is why I have this relationship for the charge density. Now if you write this expression, I'll take case 1. Case 1 is what? I am taking x greater than or equal to minus WP and less than equal to 0. So what I get? DE is equal to minus rho. This was plus. Why plus? Because minus get cancelled out. So DE equal to rho by epsilon integration dx plus some constant of integration, or I can rewrite it like integration Q N A, minus sign is there, so this will be minus by epsilon into dx plus constant of integration, or I can rewrite it, and this is now E not D, D by A, because I have integrated it. So this gives what? This is equal to minus Q N A by epsilon into x plus constant of integration. Now this is the now I have to find what? C1. And remember, whenever you do integration, that constant of integration can be obtained by applying the boundary conditions. What are those boundary conditions? Let us see. Here, this depletion layer is behaving like a parallel plate capacitor with negative charge on this side, this plate you can say, this side, positive charge on that side. When it is behaving like a parallel plate capacitor, the electric field in a parallel plate capacitor exists only between the plates. The electric field on either side outside the capacitor is always zero. You should remember that concept of electromagnetics. I repeat, electric field outside a parallel plate capacitor is zero. So if you consider just like a parallel plate capacitor, electric field on this side is zero. Why? Because there are no stored charges here. Electric field on this side is zero. There are no stored charges here. So now that is the assumption we carry. So electric field E is assumed to be 0 at the boundary, at where, that is our assumption, at x equal to minus Wp, that is the assumption you are carrying. So this gives 0 equal to, now you put minus Wp, so Q and A Wp divided by epsilon plus C1, or C1 is equal to what? Minus Q and A Wp by epsilon. So you can put this in this equation. So what do we get? E is equal to minus Q and A by epsilon into x minus Q and A Wp by epsilon. And what I find here is, what is this? This is y is equal to mx plus c. That is equation of a straight line. That is equation of a straight line. Y axis is what? E. X axis is what? X. M is what? Slope of the line, which is negative. So what is slope of this line? Minus Q and A by epsilon. And what is this C? C is called intercept with y axis in case of a straight line. So C is what? Minus Q and A Wp by epsilon. Fine. So that is what you have. So if you draw this variation, I'll start from here, from minus Wp. At x equal to minus Wp it is 0, and it is becoming minus Q and A Wp epsilon at x equal to 0. So you are varying the electric field from 0 to C. 0 to C, and C is what? This. Why it is going downward? Because slope is negative. So that is a straight line starting from x equal to minus Wp, because E is 0 at this point, going up to y equal to, that is C equal to, intercept with y axis equal to this. Slope of the line is this. So that is your, and this is nothing but intercept with the y axis. So this is the variation of electric field from minus Wp, x equal to minus Wp, to x equal to 0. Fine. Now let us see the case 2. Case 2 is, let us see the case 2. Case 2 is x greater than equal to 0, less than equal to Wn. So I am considering that part of the x, that range of the x, and we'll see the variation in electric field. And you know, for this range, what is rho? That is Q and D by epsilon. Therefore, E will be equal to what? Rho by epsilon dx plus constant of integration now, that is C2. This is nothing but Q and D by epsilon dx plus constant of integration, or you can write this is equal to Q and D by epsilon into what? That is x plus C2. And again, what I assume? Let E is 0 when x is equal to plus Wn. So this is what you have. Now, why? Because I told electric field is 0 outside this. So from this boundary, that is the boundary condition x Wn, it becomes 0 at that point. So what I'll have, this gives 0 equal to Q and D by epsilon into Wn plus C2. So C2 is what? Q and D by epsilon into Wn with negative sign outside. Put it in this equation. So this gives electric field variation will be equal to D by epsilon x minus Q and D by epsilon Wn. Again, that is equation of what? A straight line. Y is equal to mx plus c. What is m? That is slope of line, and that is Q and D by epsilon. What is c? That is intercept with y axis, minus Q and D by epsilon into Wn. A straight line of positive slope, that slope, and at x equal to Wn it is becoming 0, and at x equal to 0 That's at x equal to 0, you put x equal to 0 here, E is equal to this, but electric field is continuous from here to here, so it will be a straight line of slope q and d by epsilon, that is positive slope, and it is becoming 0 at x equal to wn, and this is E max, that is maximum value of the electric field. So what I conclude here, maximum electric field, and maximum electric field occurs at the junction, that is also called metallurgical junction. So electric field is at junction, and that value of the electric field at the junction is equal to E max is equal to, if you compare these two equations, this is coinciding with both the lines, so this was equal to minus q and a by epsilon into Wp equal to minus q and d omega n by epsilon. This is your maximum value of the electric field, and it is important expression as far as exam is concerned. There were questions on this expression in past. I hope you will remember it. Now if you compare these two, so what I find here is this and this get cancelled out, so this gives NAWP is equal to ND into WN. This is rather very important relation. I repeat, the charge density on P side multiplied by width of the depletion layer on P side is equal to charge density on N side multiplied by width of the depletion layer on N side. That is what you have. So I hope you will remember the relationship. Now we will see the next part of this topic, that is variation in the potential. Variation in potential across the junction. We will see the variation in potential. We have already seen the value of the potential barrier across the junction. That was in the previous expression we have seen. Now we will see the variation of the potential. So let us see that variation. The electric, we know what is E is equal to minus dV by dx. I repeat, we are doing what? Variation of V across junction. So this is E is equal to minus dV by dx. I'll take previous case, x greater than equal to minus Wp less than equal to 0. That is what we will be considering first. So this gives electric field equal to minus dV by dx equal to, that was minus q and a by epsilon into x minus q and a by epsilon into Wp. That was the expression of electric field for this range of x. So from here you get equal to minus minus and get cancelled out, q and a by epsilon into x dx plus q and a by epsilon into Wp into dx plus some constant of integration. That is your assumption. So what do we get? This is equal to q and a by epsilon into x square by 2 plus q and a by epsilon into Wp into x plus C1. That's it. Now I have to find the value of constant of integration. Remember, electric field is 0. That is from the electromagnetics, but potential across the junction may be like this. Please see this. Either you can draw it like this, you are taking from certain value, it is 0 at junction. You can assume the potential at junction equal to 0. Potential, remember, is always taken with respect to a reference. When you measure the potential at a point, that is always taken with respect to some another point. So I'll assume that this point is at 0 potential. and now we will see, so this is at zero potential, this is what I am assuming, and now I will see the variation. So my assumption is let V is equal to 0. That means I am taking this point as the reference for potential, and I'll see the variation up to this point. If it is 0, then it will be this point V0, that is potential barrier. So here let V is equal to 0 at x equal to minus WP. But remember, it depends on the textbook you read. Some books may be taking some value of this, maybe V0 by 2. Here the textbook I referred is given to be 0 at this point. So it varies. Reference may vary from book to book. So here it is 0 at x equal to minus WP. That is my assumption. So if it is this, put x equal to minus WP here. So this gives, to find value of C1, Q and A WP square minus WP square is WP by 2 epsilon plus, and it will be minus Q and A WP square by epsilon plus C1. C1 equal to, this will, if you see everything is common except half, so it will be Q and A WP square by 2 epsilon. That's what you have. Put this relationship in this. So this gives the potential V will be equal to what? I put this in this equation, Q and A, Q into N A by 2 epsilon into x square, or I'll take x square by 2 rather, plus Q and A by epsilon into WP x, then plus Q and A WP square by 2 epsilon. That's what you have. And if you take, you can take something common out of this complete expression, and that is V equal to, I can take this outside, Q and A by 2 epsilon as common. If you take it common, you will get x square plus, what will be there? That is 2W, this is P into x, and what will be there? WP square. That's what you have. And this is nothing but Q and A by 2 epsilon x plus WP whole square. That is the value of V, or not value, expression of V for this region, that is x equal to minus WP to x equal to 0. That is the variation. I'll say, I won't say this is important, but you should remember if it is possible. As far as exam is concerned, there is least possibility of the direct question on this. There can be 1 mark question on the figure. Now, let us take case 2. Case 2 is what? That is x equal to from 0 to Wn, that is width on the n side. So I will be taking case 2 now. Case 2 is x greater than equal to 0 less than equal to Wn. Now this gives, again just try to recall, E is equal to what? Minus dV by dx, and this is equal to, can you recall the expression please? Q and D by epsilon into x plus, that was minus, not x, minus Wn. That's what we had in case of your electric field on this side, that is this expression. So now this gives what? V equal to, I'll write it like this, V equal to minus sign on that side, Q and D by epsilon. I hope I can integrate it directly. Q and D by epsilon minus sign into x square by 2, then plus Q and D by epsilon into Wn x plus constant of integration, that is C2. That's what you have after the integration. Now just try to recall potential on this from minus W, that is minus W P to plus W, and that is what I am trying to see. The variation of this potential when it is 0, it is having some value, and what is it is X minus WP, it is 0. So it is varying like this sort of variation, and for the further part it has to start from here. It has to start from here. Why? Because potential is a continuous function, and potential rises when you move from negative charge to positive charge. Remember this. When you move the charge, unit charge, from negative to positive, there is increase in potential energy. You are moving against the field, you are moving unit charge against the field. When you move unit charge against the field, you increase the potential energy, that means potential. So here potential is increasing, so at this boundary potential must be same from this expression. Why? Because it is for positive value of X, and from this expression for negative value, because it is the common point. Potential is a continuous function. So at, I'll say at X equal to 0, is this and this must be same. I'll say Q and A by 2 epsilon WP square is equal to, now put X equal to 0 here, that is C2. This becomes 0, this becomes 0 because X is 0. So now I'll get variation of V equal to minus Q and D by 2 epsilon into X square plus Q and D by epsilon into W and X, and now you write this C2, replace this C2 by this, so that is Q and A by 2 epsilon into WP square. This is your variation of potential for X equal to, or X from 0 to Wn, and this is nothing but this. And when X becomes equal to W, your potential barrier. At X equal to Wn, what is V? V is nothing but V naught, and that is known as what? Potential barrier of what? Of the junction. So this gives, put X equal to Wn here, put X equal to Wn in this equation, you get minus Q and D by epsilon 2 epsilon into Wn square. Why put X equal to Wn here? So plus Q and D by epsilon into Wn square, and put this plus Q and A by 2 epsilon into Wp square. So you can simplify this relation now. This gives V equal to, that is Q by 2 epsilon into Nd Wn square plus Na Wp square. This is your potential barrier. This is important expression, remember it if you can. There can be question in GATE exam, not in engineering services. But till now no question has appeared, but from this topic as a whole, questions are appearing in GATE. Questions have appeared in past and there will be appearing in future as well, as far as trend is concerned now. So this is your potential barrier. So if you draw the variation, if you see the variation, so this will be V naught here. So potential is existing from this. In some books, if you take it minus V naught by 2, if you take this as reference, it will be like this. You take minus V naught by 2 here, it will be plus V naught by 2 on this side. It depends on the book to book. It may be varying. And in some questions in past, you will, they have shown this potential to be positive. How can it be positive? If you are moving from this side to this side, from P side to N side, from N side to P side, potential is positive. You are moving, I'm sorry, not potential electric field. If you move, if you take N this on this side and P on this side, you will be moving in the direction of electric field. So electric field will be positive there. So this part may be negative when you move from P to N side. You are taking this side as negative x-axis, this side as the positive x-axis. Then E will be negative. I repeat, if you take this as N and you take this as P, so what is positive x-axis on P side? Or P is placed on x-axis sides. Then when you move from minus x-axis to plus x-axis, this will be direction of the electric field. In that case, it will be reversed. So this will be positive. So that hardly matters. But this figure you should not get confused, because in textbooks it is given like this, but in exam, in the question, it was given like this. So that hardly matters. If it is given like this, that means you are placing what? P on negative x-axis and on positive x-axis. And if you are given like this as electric field, that means N is placed on negative x-axis and P is placed on positive x-axis. Otherwise, all the mathematical relations are unaltered, will be remaining same. That's it. So I hope the concept is clear. Next topic we will see is the width of the depletion layer. So that is important topic as far as exam is concerned, width of the depletion layer. So I'll drive the expression of width of depletion layer in the next video, and after that we will discuss the different type of questions. But I will be covering the topic first, that is the width of the depletion layer under open circuited condition, under reverse bias conditions, then forward bias conditions, and then we will see the numericals which have appeared in gate. But this topic is very, very important as far as gate is concerned. So there is always possibility of question on this topic in gate exam. I hope the concept is clear. So wait for my next video, that is for width of the depletion layer in open circuited PN junction. Thank you.